So now we've talked about equivalence relations and seen when a relationship, seen what's required for a relationship to be an equivalence relation. Equivalence classes group elements using equivalence relations. So take a look at this set. 1/2, 2/4, 3/6, -1 over -2, 50, 100th. These numbers are all equal to one another, right? 1/2 is equal to 2/4. 2/4 is equal to 3/6, right? You just factor out the 3 from the numerator and denominator. The 3's cancel and you're left with 1/2, and so on and so forth. In fact, every rational number has an infinite number of numbers that equal it. Right? And this is because equality is an equivalence relation. So what an equivalence relation does is, given a set, for example, all real numbers, it's going to partition those elements in the set into equivalence classes that are equal to one another. So for example, we can say the equivalence class of 1/2 equals the set of 1/2, 2/4, 3/6, and so on, as listed above. And we can say the equivalence class of 3 is going to have 3 over 1 and 6 over 2 and 9 over 3 and so on. So what's typically done is we define an equivalence class and put brackets around it. But it can be any element. We can pick any one of these elements to be in those brackets. Especially in a situation like this, I'm going to pick the most simplified element, but some sets that's not really an option. Okay, so if we have a set A and an equivalence relation R, we can say the equivalence classes of A are, I'm going to call it this bracket A, where for all x in the set A, that little x is related to A. And this only works since we have an equivalence relation. All right? If R wasn't an equivalence relation, this would not work. So if we're given this set A, shown here, we might want to ask how many equivalence classes are there under the equality relation. Right? Because there's lots of different relations that can be held over a class. We're only looking at the equality relation. So I'm going to start by grabbing the first one, 1/2, and what is it equal to? Well, itself is going to be in there. And what else in this set? Coming along, I'm going to see that 2 over 4 is really the same as 1/2, right? And then the next element, so let's do, it's going to be 1/3. I'm just going to grab the next element in the set. And it's going to contain itself. And then what else? Well, 2/6 is equal to 1/3. And 3/9 is equal to 1/3. So these are both equivalence classes. Grab the next element, 1, and this is going to be equal to itself, and we have 2 over 2, and that's it. And then finally we have our last element is a 2, and it's all by itself. So there are 4 in this case, 4 equivalence classes. Over set A using the equality relation. Okay, now we're looking back at the Boolean circuits. In the last video, we talked about these Boolean circuits and how this definition of circuits having the same I/O table as each other is an equality relation. Or excuse me, an equivalence relation. Excuse me. And so we want to know how many equivalence classes there are under S2. And this is all circuits with exactly 2 inputs. Okay, so each equivalence class will have all the circuits. Will have all the circuits, all the 2 input circuits. That share the same I/O table. Right, so they'll have the same inputs and the same outputs. Okay, so let's look at a 2 input I/O table. If we have input 1, input 2, and our output. Right, these are the 4 possible combinations. And so we've got 4 possible outputs. So this could be 0 or 1. Let's call it 0, 1, 0, 0. But each of these is binary. It means each could be one of 2 digits. In the next module, we'll talk about how we get this, but what that means is there are 2 to the 4 possible outputs in this scenario, and that is. So what this idea of an equivalence class is good for is it really helps divide up whatever set we're looking at into things that are equivalent to one another. Right? So every Boolean circuit with 2 inputs that has the same set of outputs, we can call that equivalent to one another. If we look here at these numbers, we can say that 1/2 is roughly equivalent to 2/4 using the equality relation, or that 1/3 is equal to 2/6. Right? So this is we've divvied the set up into equivalence classes where everything within the class is equivalent to one another.